Hey guys, welcome to the first video of Chapter 2 of our organic chemistry class. This chapter will be on acids and bases and functional groups. This first video will be on, in particular, intermolecular forces, which I think is, again, some more review for you guys from general chemistry. But we will be using some examples and sort of an organic standpoint to kind of connect everything together. But again, this should hopefully be sort of a review for you all. So, talking about these intermolecular forces, right, they sort of rely on the interactions between molecules, right? And this has a lot of different aspects in chemistry, right? Melting point, boiling point, solubility, crystallinity, they all depend on the strength of these interactions. So let's look at the first type of interaction, dipole-dipole. And if you remember from our conversations about dipole moments a few lectures ago, you'll remember that from a dipole moment there is a partial positive and partial negative charge. So if we look at this molecule here, formaldehyde, right, we know that oxygen is more electronegative than carbon, so when we draw our dipole moment, it's going to look like this. And carbon's a little bit more electronegative than hydrogen, so we see the dipole moment there, and overall the dipole moment is pulling towards the oxygen end of this molecule. So we can say that the oxygen is holding a lot of this partial negative charge, and we can say sort of towards the end of the molecule here, or even on the carbon would be fine too, is a partial positive charge. So when we're looking at dipole-dipole interactions between molecules, the way we might draw it is to sort of orient it like this. Where we have these two different molecules of formaldehyde kind of pointing towards each other, and right because of those partial negative, partial positive charges on the molecule, it sort of orients itself in this fashion, and we can say that we can do this sort of dotted line here to show that there is an interaction here, right? That partial negative on the oxygen is interacting with that partial positive on the carbon, right? So the electron cloud of each of these molecules is sort of being warped in a certain direction, right? With more electrons pointing towards the oxygen and less away from the carbon end of the molecule. So I've only drawn two here, but if you would imagine a bunch of these molecules together, they would have that sort of favorable interaction, where they would be all sort of congregated together. So for next example, and it's very similar to dipole-dipole, we're going to be talking about ion-dipole. So right, ions are charged atoms or molecules right, with a positive or negative full charge. And a dipole moment, again, is that partial negative or partial positive charge. So if we were to say, okay, let's put sodium chloride into water, right? Aqueous, kind of redundant, but whatever. What would that look like, right? From a molecular standpoint. Right, so sodium, very positively charged, right? When we look at water, it should be hopefully a pretty familiar example to a lot of you, right? Water, right, H2O, it's going to have that, not only a lone pair, sure, we can draw that in, but more importantly, right, it has that dipole moment where the oxygen is much more electronegative than the hydrogens, right? So we see that dipole moment pulling towards the oxygen, giving it that partial negative charge, and the hydrogens with a partial positive charge. So in a solution, right, we put sodium chloride in solution, there's a bunch of these water molecules kind of surrounding the ions and forming these interactions, right? To sort of quote-unquote stabilize that positive sodium so it's not just hanging out in solution by itself in charge. So these water molecules are going to be sort of stabilizing it. Conversely, of course, with the chlorine, the negatively charged chlorine, we're going to have sort of the opposite situation where the partial positive end of all these water molecules are going to be surrounding them. right? Because again, the hydrogens all have that partially positive charge, right? And so this is an ion dipole interaction, right? The dipole from the water with the partial positive and partial negative end are going to stabilize those fully positive and negative ions in solution. So the next type of force is the London dispersion forces, and this is almost sort of a sort of catch-all for really non-polar molecules, right? So we think about water, we think it's a really polar molecule, right? It has a very polar covalent bond. But for a lot of molecules, like mostly carbons and hydrogens, there's not really any significant dipole moments happening. So when you think about something like, oil, or you think about, octane or pentane, right, those sort of higher end hydrocarbons that are liquids, how are they staying together? Why are they just flying apart? It's because of these London dispersion forces, which are temporarily induced dipole-dipole forces. So, to give an example of that, let's do pentane, C5H12, right? So it just looks like this. And so if we had a bunch of these in solution, right, all these just carbon and hydrogens, right, how are they all sort of staying together, right? What's keeping them together in that liquid form? And it is entirely from that temporarily induced dipole-dipole moment. So if we were to draw out, let's say, the electron cloud, right, so just like that sphere of electrons all around the molecule. So we're just sort of simplifying pentane now to something like this, right, just a sphere of electrons. What would happen here, right, is all these pentanes come together. Instead of having that negative charge in that those electron clouds sort of evenly distributed across the entire molecule, what ends up happening is that things get sort of warped, right? So you might have a negative end pushed this way and the positive end pushed this way, right? So the general flow of electrons might be sort of in this direction, right? The electrons are getting pushed this way, right? And so that's going to change the other molecules here as well, where you have the electrons being pushed to one side, right? And that sort of influences the other side, right? So if you have a positive end of this pentane, this electron cloud being pushed one way, then the other portions of these molecules are going to sort of respond appropriately, right? Again, these are temporarily induced. These can change in solution. If you have these pentane molecules flying around, the electron cloud is going to be warping a lot. It's essentially, you can think of it this way too, where the electron cloud is being flexible, right? It's being malleable, where it'll kind of change in one direction then to another, sort of keeping everything together. So again, London dispersion forces are kind of a sort of a catch-all for something that isn't, as obvious as dipole-dipole moments, ion dipole moments, or hydrogen bonding, right? So for the last example, we are going to talk about force hydrogen bonding. And so this is when you have a partially positive hydrogen, right, from a dipole moment, attracted to more electronegative atoms of other molecules. So to give you an example that isn't just water, let's look at ammonium chloride. Right, so looking at ammonium chloride here, where we have the dipole moment overall pointing towards, right, the nitrogen. So in this case, the nitrogen end of the molecule is partially negative, and the hydrogen end are all partially positive. So what ends up happening, if we have a variety of ammonium atoms in here, right, we're going to be forming these hydrogen bonding interactions, right, from one hydrogen to that nitrogen, right, again, because of that partial negative, partial positive interaction. And what's kind of important to note, too, is unlike with dipole-dipole interactions, hydrogen bonding, H bonding, is a much stronger dipole-dipole interaction. And it's very, very important biologically too, so it's kind of why it has its own category. So this sort of bonding here, even though it looks, the way I've drawn it, pretty identical to dipole-dipole interactions, it is a much, much stronger interaction than dipole-dipole, right? It's not a true bond like ionic or covalent, but it is a very strong type of intermolecular force. And this has a whole bunch of implications, right? So, for example, we talk about boiling point. This directly relates to intermolecular forces. So, in the case of water, right? Actually, I'll draw this a different way just to make it more suggestive. Right? Water has these two OH bonds, right? That can do hydrogen bonding. So the boiling point of hydrogen is 100, right? 100 degrees C. But if you look at another molecule, ethanol, right? This molecule only has one hydrogen bond, and the boiling point is actually much lower, somewhere around 80 degrees Celsius. And the difference in boiling point can be explained by the hydrogen bonding, right? The water can do more hydrogen bonding in solution than ethanol can, right? This only has one hydrogen bond, so it's harder to break apart water in solution because of all the hydrogen bonding going on with it. But ethanol can break apart easier, so it requires less energy to vaporize it, right? And this sort of principle can also be applied to solubility. When we're talking about, dissolving sodium chloride with water, right? Both water and sodium chloride can be considered polar, right? There's a very clear positive end and a negative end to these molecules. So in that case, they can solubilize each other. And similarly, in the case of nonpolar solvents, where primarily London dispersion forces will take place and keep them together. So if we were to look at, for example, looking at pentane again, which is liquid, and we try dissolving it into water, what would end up happening is, if we had a bunch of water molecules, they would be sticking together through hydrogen bonding, and pentane wouldn't really be able to stick into there, right? Because water would much, much prefer to be hydrogen bonding with itself than participating in London dispersion force interactions with pentane. So that's why even if you try to drop oil into water, the oil, those oil molecules are going to end up sticking together and form almost like little oil puddles on the water surface, right? Because of that difference in the intermolecular forces that are going to be holding these two different types of molecules together. So this is an example that we'll end up doing in lecture. Take a look at it and see if you can try to figure it out on your own, but we will be going over it in lecture next time we meet up.